end of, I think, hopefully it is the end of COVID season.
Yes.
So hopefully, I don't know, slowly we are starting to open our institute campus. How about there? Have
Yes.
you started classes and labs in person?
Yes, sir. Yeah, yeah. Almost. Yes, sir. Almost all of the classes has been started offline. So
Okay,
students are
great.
coming in the institution. Although the attendance is not so much good, but
Okay.
around 40-50% students are coming to the classes.
बहुत अच्छा, बहुत अच्छा. So our in-person classes have not started yet. I think we will start
Yes.
in January, hopefully.
Yes, sir.
So your first year has started.
Actually, that is governed by AICTE. So that
Uh,
will actually there is the intensive program nowadays. The actual classes will start from 1st of December. So within 4 or 5 days, the actual classes will be started for the first year.
okay, I see. I see. Good. So our hopefully our first year classes will also start sometime in December, and they will start in person. But the regular other BTech and MTech classes will start in January, and they will start in person.
Yes.
But there is a lot of resistance from the students. They don't want to come back to the campus.
Sir, I think online classes are still running.
So now it is major exams are going on. So all classes are
Yes.
over. So I think we will have we are having some bridge courses scheduled in the month of December for the laboratories, especially for hardware labs. So those
Yes.
students will be doing those labs which could not be arranged online. We are trying to
Yes.
conduct those labs in person. So those students are have been called back to the campus. So, but this situation is dynamic and evolving. So every week we get to know some new development that has happened. Something has been moved forward. Something has been moved backward. Now there is a problem of
Yes.
pollution.
Yes, sir. Yes.
So because
I
of
have heard
pollution,
in
yeah,
with
yeah,
some
very bad.
newspaper and some news that there is the that schools are has been closed for a week, I think.
Yeah, no, schools have been closed indefinitely in Delhi. So our Delhi kids are that were very unfortunate. They are not going to school. I think rest of India schools have started.
Yes, sir. Yes. Here also in Rajasthan, almost all the schools are open with 100% capacity. So there is no bar
Hmm.
kind of thing. Uh, Even government has also, I mean, there is no restriction on the institutions, on the schools that they run the online classes. They may call all the
Okay.
students offline.
Okay. Okay. Great. So,
Also,
uh,
so last 2-3 days, actually, the cases has been increased. Actually, in around 1 week back, there was only 30-40 active cases were there in Rajasthan. But we
hmm.
have seen in last week that in today's newspaper there is about 100 active cases are there in Rajasthan. So maybe it will increase because we are not sure about this one.
Yeah, कुछ तो impact आएगा. Some impact will be there from the festival season. And also
Yes.
now, everywhere you go in Delhi, people are just not wearing masks and not following any social distancing rules. So trade fair is going on.
Yes.
That is totally
Yes, sir.
completely crowded. All the markets are crowded. So कुछ तो उसका effect आएगा.
Yes. So I think, sir, the participants are joining. So meanwhile, I think we can start the presentation. If anyone of the participants has any kind of query, they can ask in the chat box, or even they can interact in between also in the presentation. So
Yeah,
I
yeah, sure, sure.
so good afternoon, all of you. I formally welcome Professor Nilanjan Senroy, sir, from IIT Delhi, from the Department of Electrical Engineering. I want to briefly introduce Professor Nilanjan Senroy, sir. Actually, I had also worked in my PhD under the supervision of Professor Senroy, sir. So it's my pleasure to have you, sir, in this 5-day online integration of renewable energy systems, FDP. So here actually Nilanjan Senroy sir has got his MS and PhD degrees from Arizona State University, Tempe, USA. He also has postdoctoral experience at the Center for Advanced Power Systems, Florida State University, Tallahassee, USA. Sir is currently a Power Grid Chair Professor in the Department of Electrical Engineering, Indian Institute of Technology, Delhi, India. Uh, Sir's research interests include power system stability and control, dynamics, modeling and simulation of wind energy conversion systems, and signal processing techniques in the power system. With this one, sir has also many of the projects. Sir is also associated in many of the projects. So, with a very rich academic background, I request Professor Senroy sir to please present himself. So,
Okay, thank
sir,
you.
can you can start, please?
Okay, thank you. So I hope I'm audible, and let me see how to share this slide window. Okay.
Sir, at the bottom there is up arrow. There is one
Yeah,
arrow
yeah,
at the
yeah, yeah.
bottom
I can see
of
that.
this. Yes.
Is it visible?
Yes, yes, sir. It is being shared. Yes, it is visible, sir. All
Oh,
right, sir.
okay, okay, great, great, great. Okay, so good afternoon, everybody. And first of all, thank you very much for inviting me to for this lecture session. I was going through the list of other experts who are invited to deliver lecture, and it is very impressive. And many of the names are very familiar. So I think there are a few very small group of people in India, unfortunately, today who are working on this very, very important and critical area of renewable energy integration into the power grid. This particular domain, this particular topic requires a lot of skills from electrical engineering, from systems theory, from control theory, from mechanical engineering, and of course a very strong mathematical background. So that kind of a mix of skills is not very easy to find. However, in India we have a small but dedicated group of researchers who are working on this, and they have been able to make very significant contribution to the understanding of the grid operations and control in the presence of large scale renewable energy integration. And most of these researchers are known worldwide, and their contributions are acknowledged worldwide. So, Dr. Ganesh is also one of them, and I'm happy to see that in Bikaner there are many of these faculty who are today engaged in this RE integration research in RE integration, and they are also very well known in India as well as abroad. So, I work in the area of grid dynamics. I am not really a renewable energy person by training. I am a power grid engineer by training, and renewable energy is one of the biggest challenges confronting power grids today. And so, therefore, I also work in the area of renewable energy integration into the power grid. I do not work in the area of renewable energy production as such. That requires a completely different set of skills here. So today my presentation is going to be on the impact of renewable energy integration on the way the power grid behaves, and what are the actions that we can take today so that our grid of the future is secure and reliable, even when the renewable energy integration, integrated renewable energy is a significant component of the total generation mix. So I hope all of you are aware that the India has set very, very strong, very, very ambitious targets. I think in India, the target is about 175 gigawatts by 2022 and about 450 gigawatts. Well, these numbers keep changing. The other day in the newspaper, I read it was 500 gigawatts by 2030. So 450 gigawatts and 500 gigawatts are very big numbers. 450 gigawatts is currently the total generation installed capacity in India, and it is expected that by 2030, 450 gigawatts will be the total renewable energy capacity in India. So India is leapfrogging towards the goal of rapid decarbonization of electricity. And this is, of course, in line with the Paris Agreement on Climate Change and the nationally determined contributions pledge that all countries have taken in the Paris Agreement for climate change. So once this goal is achieved, the generation mix portfolio of the country will be drastically changed. So to achieve this target and in a sustainable manner, and to ensure that we do not collapse under the weight of this target, we need to develop an organizational ecosystem that involves all the necessary stakeholders and decision makers, and the policy and regulatory actions they all have to be aligned to provide a smooth conduit for this transition. So before I go ahead with this topic, I wanted to talk a little bit about a slide, which is one of my favorite slides that I have used in many other presentations. This slide is an old slide, about 10 years old, and it is giving some statistics about the energy future of our country. You can see this slide I have taken from the IEEE Power and Energy magazine, June 2012 issue, and it shows that our India. You can see that different parts of the world have been compared against each other in terms of the population, in terms of the total primary energy supply, in terms of the number of units per capita annual consumption, and the tons of carbon dioxide emissions per capita. So the world average, if I look at the electricity, just the third column I'm looking at, the number of units consumed annually per capita, India's number is 597 compared to the world average, which is 2,730. Africa is 561, and so we are just marginally above Africa, and we are lower than the average for Asia. If you look at the total primary energy supply, which is different from the amount of electricity consumption, because it also includes firewood or any kind of primary energy that is used, gas or firewood, anything. So our number is really small. It's like 580 kilos of oil equivalent per capita annually, and this number is lower than Africa also. So we are really a very energy hungry country. Our energy consumption is very low, and consequently our carbon dioxide emissions in terms of tons of carbon dioxide per capita is also very low. Of course, if you multiply the number in the last column with the number in the first column, then the total carbon dioxide emissions from our country is very, very big, and it has a very significant impact on the environment. So if you look at the total number, it is very bad. We are emitting a huge amount of carbon dioxide, but if you look at the per capita, then it's very small, and that gives an indication that we are a poor country. So the electrification in India is currently 100% as per the Ministry of Power. But of course, this number is very, very dicey, because a village is said to be electrified only when, as soon as you have a transformer located and connected in the village, and some X percentage of households having received supply. So when I say 100% electrification, I don't mean that 100% of all households in India have electricity. It is as per some government standard that it is 100%. So definitely a large number of people in our country, especially in the rural areas, are still living in the darkness and their lights have not yet switched on. So in order to switch on the lights, we need to find out alternative sources of energy, alternative sources of electricity. And on the right hand side, you can see what are the sources of energy. So you can see coal, we have a lot of coal. However, that coal is being consumed at a very, very high rate. In fact, if you're following the news, a few months ago, in October, not a few months ago, in October rather, last month, there was a big crisis in our country because the amount of coal that was being produced was not enough to meet the energy needs of our country. So traditionally, while the load in any city or any town or any state, the load may peak during summer or winter, depending on the weather there and the nature of the appliances connected. But in India, the monthly energy peaks in October, and that is usually because of the festive season. So the amount of coal that is required in the month of October is usually very high. So the rate at which our coal consumption is increasing is alarming, and I believe that in the next 30 to 40 years, our entire coal supply will be exhausted. So therefore, we need to very quickly come up with alternative sources of energy, and these include nuclear, hydro, wind, and solar. We do have a lot of solar potential, enormous potential. However, the technology is still maturing, and we still have some way to go before we can have a reliable technology to produce solar photovoltaic arrays. Similarly, in our country, the wind turbine generators are still all onshore. The offshore potential has not been estimated. However, we do have a lot of potential for wind. So, based on the wind and solar and small hydro, of course, small hydro is also considered to be renewable energy in India. So, based on these numbers, the only way for us forward is to go for renewable energy integration at very, very large scales. I hope my slides are changing.
Yes, sir, it is changing. Yes,
Yes,
sir.
yes. Yeah, yeah. Okay, okay, thank you. Right. So when you have such high levels of renewable energy integrated into the grid, we need to decide how much flexible our grid is. So I will focus on the grid. I will not focus so much on the generation aspect, generation part of it. So I will just quickly remind you of some key enablers of renewable energy integration in India. Enablers means strategies, regulations, norms which have resulted in and which are resulting in high levels of renewable energy integration in India. So, what are the current strategies that have been introduced in our country? So, the first strategy I wanted to talk about is the primary frequency control with droop that has been mandated for state and privately owned thermal generators. And this basically means that the governors that are located with these thermal turbo generators must be allowed to respond to system frequency changes. This will help to stabilize the frequency in the case of a sudden unexpected load generation unbalance. Then about 9,000 circuit kilometers of transmission lines have been set up, and these are aimed at evacuating renewable energy from the southern and the western parts of the country. And this is called the Green Corridor Project. Then we have the Reserve Regulatory Ancillary Service, which provides for the utilization of surplus generation to control the frequency, to manage network congestion, mandatory. It is mandatory to decongest the network, and of course to secure the current operating state of the grid. So this has been enabled for large interstate generating stations. Then the concept of renewable purchase obligation has been introduced, and it is very successfully implemented in our country. It mandates that a minimum quantity of energy must be purchased from renewable energy generators. Then, in order to reduce the cost of generation, a pilot project of some key interstate generating stations has been initiated for security constrained economic load dispatch, and I'll just talk about that in a little while. Similarly, some pilot AGC projects have been initiated by POSOCO and NTPC in order to demonstrate the capability for secondary frequency control of the grid. So the initial plan is to start with the ISGS generators, the interstate generating stations, the big ones, the big generators. And finally, the idea is to expand this reserve availability to all generators that are scheduled by the regional load dispatch centers. There is something called the deviation settlement mechanism. So that has been going on for some time, but that mechanism has some very key drawbacks. And I invite you to read a report that is there online in the public domain that was taken out by the CERC expert group. And many of they have suggested some reforms in the deviation settlement mechanism in order to integrate renewable energy. So, for instance, they advocate better planning of reserves, then improved resource forecasting by the RE power producers. Then the electricity market needs to iterate more in order to discover better prices. So there are a lot of other reforms that have been suggested by this CERC expert group. Then there was another report by Central Electricity Authority that recommends to reduce the minimum thermal load for thermal power generators from the current 60% to 50%. And this is a very revolutionary idea because currently the boilers are not able to operate stably at loadings below 60% of the capacity. And that is because the flame dies away. The flame stability is not there. So this is basically a thermodynamics problem, mechanical engineering problem. So using plant automation, overcoming boiler limitations, the way you are controlling the flue gas, the way you are controlling the quality of coal that is introduced into the boiler, you can actually reduce the minimum thermal load of these generators from 60% to about 40%. Germany has done that. In fact, Germany has demonstrated their thermal boilers to operate at about 36-37% of their rated capacity. We need to set up bulk level energy storage systems, like for instance, pumped hydro energy storage systems. These are very, very useful because they have very fast ramping capabilities, peaking capabilities. And when the active power requirement is not there, then these generators, the generators that are associated with these pumped hydro stations, they can be run as synchronous condensers to support the grid voltage by injecting reactive power. And of course, discontinued thermal power plants, which are polluting. For instance, in Delhi, Badarpur thermal power station was polluting and it has been stopped now. It has been discontinued. So these discontinued thermal power plants, there's a plan to retrofit and convert them into synchronous condenser stations and this can help manage the reactive power unbalance in the grid. So these are some of the key enablers in order to allow the grid to maintain its flexibility while um, integrating renewables. So here you on the screen you have three diagrams, pentagons, and these pentagons refer to three different countries. So these are talking about the sources of flexibility for these countries. So in one diagram, you can see very clearly that the green figure is skewed towards interconnections. So before we go there, I'd just like to say that this is a report that was taken out by National Renewable Energy Labs in USA, and they talked about the key sources of flexibility. These key sources are interconnections, hydro, pumped hydro, combined cycle gas turbines, and combined heat and power plants. So when you have a wind penetration, a wind generation penetration of 47.3% in a particular country, then it is found that for that country, the key sources of flexibility are hydro and combined cycle gas turbines. So therefore, obviously, that country has a lot of hydro and gas reserves. Similarly, some other country, for instance, in Europe, this country has a wind penetration of 36.4% into the grid, and the key source of flexibility is the interconnection. In another country, the key source of flexibility is the combined cycle gas turbines only, and you can see that it is heavily skewed towards CCGT. So some of these countries are like, for instance, Ireland. Ireland has a very high gas reserve, so their flexibility comes from combined cycle gas turbines. So in India, this is a small exercise that was done in our country, where based on the CEA report of January 2019, which talks about the flexibilization of thermal power plants in order to support the renewable energy integration. It is found that the coal thermal in our country is the key source of flexibility. Other sources of flexibility are, of course, interconnections and hydro, but the coal thermal is the biggest source of flexibility. So this is a new idea, and this requires this requires enabling the thermal power plant to operate at very low loadings, so that when the grid is having a large amount of renewable injection, the thermal power plants need not be shut off. They can continue to run while operating at a very low loading. So this is what I was talking about in the previous slide, the reduction in the minimum thermal load in steam boilers. So for Indian grids, it is seen that rapidly the plant load factor is declining. Plant load factor means the amount of energy it produces in a year divided by the amount of energy it could have produced during the year. So right now it has dipped to about 60% in 5 years from 77.5%. So if you look at this number a little more closely, you will find that the plant load factor declines because of other reasons also. For instance, not enough coal is available. Another reason is there is a rapid addition of conventional capacity. So more than the rate at which coal is being supplied, the number of plants is increasing at a higher rate. Similarly, because of lack of economic activity, if the electricity demand stagnates, then the generation will also stagnate. Finally, in our country, distribution systems are not able to price electricity properly, because pricing of electricity is a political matter. It's not easy to raise the cost of electricity. And so therefore, most of our discoms end up in very poor financial health. And so they're not able to pay for electricity to the generating station, generating companies. And as a result, the generating companies are idling much of the time. So based on the current trends, and extrapolation was done, and it was found that on July 19, 2021-22, probably we are going to see a very high renewable energy day, because in July there's a lot of wind. So the amount of renewable energy, renewable generation that is online would be very high. Also because it's nice weather, people would have switched off their air conditioners, they would have switched off their geysers, heaters, and so the demand would be low. And in the morning and in the evening, the solar would ramp up and ramp down respectively. And so you would have maximum peak to off-peak demand. This is a very important number to look at, the peak to off-peak demand. And I think somebody has raised a hand. I don't know how to handle this. Maybe if you have a question, please go ahead and ask rather than typing it out in the chat box. Is there a question? All right. So it was found that a peak hour ramp rate of 247 megawatts per minute was expected, and similarly the sunrise ramp down rate was about 368 megawatts per minute. So at sunrise the solar switches on, and when the solar switches on, the thermal generation, which would have been online already, has to be backed down. So the ramp down rate during sunrise is 368 megawatts per minute. And this is a huge number, tremendous number. So generally, thermal power stations have ramp down, ramp up limits of about 2 to 4% of the rating. So about a 500 megawatt unit cannot ramp up or ramp down at more than 10 megawatts per minute. So this 368 megawatt per minute is a very difficult number to achieve. So the only solution is that, because you have a large number of thermal generators and hydro generators, you must enable AGC, secondary frequency response, in order to improve the ramp rate capability. You have a lot of power converters and energy storage already online, and so these can be used to provide virtual inertia. Similarly, wind turbine generators and solar photovoltaic arrays can be deloaded to create additional power reserves so that they can contribute to secondary frequency response in AGC. And today, commercially, there are algorithms, commercial technologies have been deployed in order to enable wind farms and solar farms to contribute to frequency control. Then extensive use of synchronous condensers in order to improve the reactive power support to the grid, improve the short circuit level in the neighborhood, and finally inertial support to the grid. So we need to have a lot of rotating machines and not just STATCOMs and SVCs, which can provide both reactive power and inertial support. So at IIT Delhi, we have a Renew Center of Excellence on Sustainable Energy. Renew Center of Excellence on Energy and Environment. And this basically looks at energy, sustainable energy and climate change and environment. And this Center of so I am heading this Center of Excellence, and one of the key projects that was completed in this Center of Excellence was to look at the flexibility of Indian power grids in the space of incoming renewable energy. So it was recognized that the key vehicle of electricity supply transition is the grid. And we cannot ignore the grid. The grid has to be expanded to include newer non-conventional generation sources, And the fact that the renewable energy is not uniformly distributed across the country leads to disparity between different states and regional grids. So, grid expansion must take this into account, the spatial diversity associated with renewable energy generation. Then there is another problem of the depleted fleet of dispatchable synchronous generators. And so the system operational planning and strategies that have evolved over the years, they have always assumed that you have a lot of dispatchable generation available. They need to adapt themselves to the characteristics of renewable energy generation. So we cannot have a one size fits all approach. We must avoid, because we need to come up with location specific practices for grid planning and operation. So the two key challenges remain in our country. Number one, that unexpected fluctuations in generation can reduce grid security, reliability, and impact the operating pattern of existing conventional synchronous generation. Then significant reactive power footprint, and this may lead to voltage instability and, of course, unacceptable power factor operations. So we need to come up with a solution which must be technologically, commercially, and regulatory in nature, so that our zero cost renewable energy is not curtailed in order to make way for non-zero cost conventional generation. And that is what is happening today. Our renewable energy is being curtailed. So in the Center of Excellence at IIT Delhi, we came out with a white paper, and that white paper was authored by my colleague, Professor Abhijit Abhyankar, and myself. And this we developed this white paper based on extensive consultation with many officials in POSOCO, NTPC, Renew Power, GETCO, Orissa Power Transmission Company Limited, and so on. And we have come up with some recommendations regarding the Indian power grids. And I just wanted to discuss those recommendations in this lecture here. So one very key recommendation that we are making is the locational flexibility of the grid. We need to measure and quantify the flexibility of the grid in a location specific manner. And we also need to recognize that the flexibility of the grid is time varying. It is not a quantity that has to be recognized, that has to be measured or assessed once every 10 years or something. No, it must be periodically updated. So we need to define the flexibility of the grid. So we need to keep in mind that the variations in demand and generation setting up of new power plants, whether they are conventional or whether they are renewable, then the way the units are scheduled, then if you have changes in the network topology, some lines being taken out because of maintenance purposes or because of an unscheduled fault, then changes in control strategies, all these have an impact on the flexibility. And so this flexibility must be periodically assessed. So two different aspects of flexibility must be assessed. The first is the system strength, which is looking at the voltage stability, and the second is the system inertia, which is looking at the grid stability. So when we talk about the system strength, I hope you know that the system strength basically refers to the reluctance of the grid voltage to change in response to small perturbations such as switching on of a load or an equipment. So it is also directly related to the available three-phase fault MVA level, so short circuit strength. So Many times we make copper plate assumptions. Copper plate means, that the grid is just like a copper plate, and so the impedance at all points is the same and usually very small. Copper plate has almost zero impedance, zero resistance. So copper plate assumptions while planning the deployment of renewable energy plants is very, very dangerous and can lead to situations where a large amount of renewable energy is being injected at a very weak portion of the grid. So therefore this can actually lead to line overloading and congestion, unacceptable voltages, and very low fault levels. Eventually, this kind of a situation can lead to zone 3 tripping, inadvertent zone 3 tripping of distance relays and load encroachment. I hope you know that the um, distance relays measure the impedance, and if the impedance is measured as a ratio of the current and the voltage, then during heavy load conditions, high current and depressed voltage can result in the impedance relays tripping, and this kind of a phenomenon is called load encroachment, and this is what played a very key role in the July 2013 blackouts that were experienced in India. So therefore, we need to have a node-wise mapping of the system strength so that we can come up with the hosting capacity at these locations. At every node, we need to come out with a hosting capacity. How much power can be injected into that node? And this must be periodically updated, typically maybe annually, and if not annually, every time the grid undergoes a significant change, this hosting capacity must be remapped. Then at important nodes, we need to specify the minimum fault current levels that the grid will provide. And the fault current levels over the years at these nodes must be monitored. And if you find that the fault current levels are going down, then you need to install some equipment there in order to restore the fault current levels back to acceptable levels. So for instance, one very key source of fault current level is the synchronous condenser that can help restore fault current levels back. Also remember that grid forming converters, today a lot of people are talking about grid forming converters. These can also contribute to system fault current levels. However, at this stage, it is not very wise to rely on grid forming converters to as in my available fault current levels should be satisfactory even without their contributions. Then finally, the system strength, if it is low at some point, it must be enhanced by stabilizing the voltage using fax devices and by reducing the grid's internal impedance. So this can be achieved by modifying the dispatch so that a minimum number of synchronous generators in that neighborhood should always remain online. We can also convert retiring thermal generators into synchronous condensers. And of course, if you're looking at islanded grids, then grid forming converters can be a very key source of strength in those islanded grids. System inertia is the second aspect of locational flexibility that we talk about. In system inertia, we are, inertia, I hope you know that inertia is used in the context of system frequency and its reluctance to change due to unexpected load generation unbalance. And this is also related to the mechanical moment of inertia of the rotating shafts of all the synchronous machines connected in the system. So, with the mandate of free governor mode of operation that was mandated by the Indian Electricity Grid Code, along with further enabling of primary frequency control using minimum governor deadbands. Our frequency is relatively very stable. The lowest or the highest point of a frequency excursion after a grid disturbance is usually well regulated unless the grid is in trouble for some reason. However, one key problem that may arise in future, which is not yet a problem in our country, but it is showing up as a major problem in countries such as Australia and Great Britain, is how to manage the rate of change of frequency, the rock-off. So post disturbance, the rock-offs may exceed some acceptable numbers. So if that happens, then your turbines, the steam turbines, may trip. So therefore, today, many of these countries, Great Britain, Australia, their grid codes are saying that the new generation steam turbines should be able to withstand high rock-offs. In our country, we need to anticipate this situation, and we need to come up with synchronous machines which will be predominantly employed just to provide inertial response. Remember, local to state to national transition of the grid through interregional links, and tariff-related constrained transmission strategies. These may not always allow adequate inertia availability throughout the system. So you may have a lot of generation at one location, but the constraints in transmission do not allow this inertia to be available in other parts of the grid. So therefore, you need to distribute your synchronous machines throughout the grid. The spatial distribution of inertia in India is clearly very non-uniform. So, for instance, the southeastern regions of Uttar Pradesh, they are having large capacity thermal power generating plants. And so their inertial concentration is highest. In Rajasthan, the grid is relatively less meshed with the rest of the region. So in Rajasthan, parts of the grid will see increasingly high rock-off values as renewable energy, with more and more renewable energy integration. So therefore, it is recommended that an accurate mapping of available system inertia should be carried out periodically, and you can reduce the scope of the problem by aggregating the grid into smaller areas that share similar inertial and dynamic characteristics. And it is expected that within those areas, similar maximum rock-off levels under various dispatch scenarios would be experienced. And finally, this may also help, of course, to update the settings of your frequency-based load sharing schemes, which basically respond to rock-offs after a severe generation loss event. Once you have identified shortfalls in available inertia, corrective actions must be taken. So once again, these can be, setting up of new transmission lines, installation of synchronous condensers, identifying minimum synchronous generator dispatch in an area, as well as distributing the spinning reserves within an area in a smart way. And finally, we can always explore the deployment of virtual inertia from grid-forming converter systems. Then today in India, we have a large diversity of incoming renewable energy operators. We need to have a participative grid code. So many times we at IIT Delhi have been approached by small renewable energy operators, companies who want to set up farms, and they find that the grid code is unfair, well, in quotes, unfair. They find that the grid code does not make sense. So the whole idea is the grid code has not been developed in a participative manner today in India. Of course, you must remember that in India, we need to have a universal grid code. We need to have one grid code for the entire country. You cannot have different grid codes in different parts of the country, even though the grid flexibility is not the same throughout the country. So depending on the system strength, the voltage, the X by R ratio of the connected network, the connected generation levels, the ability of an independent power producer to influence the system voltage by injecting reactive power may vary significantly. So the way the grid code, which is universal, is to be implemented at a location may differ. So the expectations from the incoming independent power producer, independent company, the expectations will be defined in terms of how much active and reactive power reserves have to be provisioned so as to demonstrate their capability to operate under stress. So if you are saying that so the grid code says that if the farm is generating 100 megawatts, wants to inject 100 megawatts, it should have the capability to inject 50 megavolt amperes, 50 reactive MVARs also. Whether it will actually inject that or not is different, but it should be able to demonstrate that capability. Now, this 50 number is universal all over the country, possibly, but the way it will have to need to be demonstrated may differ across the country. So these kind of location-wise differences in the way the grid code is to be implemented may be considered in order to allow the diversity of incoming renewable energy operators. The second aspect that we talk about in this white paper is the operational flexibility. And here we are talking about security constrained unit commitment. It is, I hope you are all aware of what is security constrained unit commitment. It is currently not very well practiced in India. It's a powerful generator scheduling tool. This basically helps in operational planning. It decides in advance whether a generator will be on or off at a given time block. And the objective of this optimization is to minimize the production cost while satisfying the power system constraints, modeling constraints, including the intertemporal constraints, the constraints related to time. So this is basically a mixed integer programming problem. It's a little involved, but already there is some thinking going on in our country on introducing security constrained economic load flow, economic load dispatch, and security constrained unit commitment at the state level, increasing it to the central level, and finally the real-time, near real-time operations. We need to look at how to introduce economic dispatch near to systems at near real-time operations. Finally, we are talking also about the flexibility of data. This is very important because any integrated energy system planning and operational architecture will require working with copious amounts of data. You know, we have so many sensors today. These sensors collect so much of data, and this data is typically varying in structure. It is voluminous, it is diverse, uncertain, granular in nature. So previously, most of the generation and transmission assets were state-owned, and the system operation and planning was usually suboptimal. But now, because of the increasing complexities associated with regulatory and commercial power exchange frameworks, many of our existing data handling techniques will become outdated. So we need to come up with data analytics which can be vigorously applied in the grid control centers for state estimation, line parameter estimation, dynamic security assessment, situational awareness, monitoring the system strength, Then electromechanical mode metering, assessment of how the modes of the system vary, short circuit ratio and inertia estimation in real time. We need to do this in real time. So data analytics must be developed for the same. So one very commonly used sensor for this could be the phasor measurement units that are being deployed in large numbers in our country today. So there needs to be now some clear guidelines on the use and availability of the system data. System data as in what is the resistance and the impedance, inductance of a particular transmission line. Should this information be given out? Should it be kept in the public domain? If I keep it in the public domain, can it be used to attack my grid? This is the key concern, number one. Second concern is, of course, can it be used to make profit? So incoming power producers, which are independent power producers, as well as the system operator, they need to collaborate to understand the impact of the incoming technology. And so this is only possible if the utility is aware of the incoming technology. That means the incoming power producer should be ready to share details of their technology with the grid operator. And similarly, the grid operator should be ready to share information about the grid with the incoming power producers. Only then this collaboration can help in proper grid flexibility assessment. So obviously the utilities today are understandably reluctant to share smart grid data, the metering data, because this data may relate to their assets, their metering infrastructure, operational and commercial operations. However, there are ways of anonymizing this data before sharing. And once you have anonymized the data, it can be helpful for research and development of best practices. It can also bring more control in the distribution of the data, visibility, its accountability. Finally, it must be realized who is the owner of the data. If the data is collected using public funds, then the public is the owner of the data. And so this requires a change in the approach to data ownership. Data must be collected, hosted, and periodically verified by an independent agency. So this is required in order to ensure the integrity of data. So when somebody gives you data, you must be sure that the data is proper. So a lot of the metering data is unused. It just gets
Sir,
collected.
may I interrupt you? I think the slide are not changing. Am I audible?
Yeah. I'm still on that slide. Yeah. I'm still on that slide. I'm going to change the
Okay, all
slide
right.
soon. I'm still
Okay, all
talking
right.
about
Please
flexibility of
continue.
data.
Thank you.
Yeah.
Yes,
Sorry.
yes. Thank you.
I have a habit of talking a lot on a single slide only. So, anyways, so flexibility of data utilization is required. Yeah. So let's just quickly look at how the voltage and the frequency of the grid changes is affected by the fluctuations in renewable energy. So here I'm showing two graphs here. These graphs are obtained by simulating wind turbine, which has been subjected to a low voltage situation. And on the right, you can see that when the DFIG, the double fed induction generators, voltage drops, the rotor current rises tremendously. And this could lead to about 4 times the rated current. You can see that 400% rated current is seen in the DFIG. And this kind of a behavior requires that the DFIGs should be disconnected during low voltage situations. You need to come up with technologies that can help your wind turbines to remain connected during fluctuations in voltage. So low voltage ride through studies are very important today. in order to understand the impact of how the wind farms and solar farms can support the grid during low voltage situations. Another thing that has been observed is the active power deviation because of the wind speed deviation. So if you have a wind turbine of significant inertia and the wind is varying continuously, then the output, the active power output also varies. However, there is a certain amount of smoothing that happens by virtue of the shaft inertia, even if you do not apply any artificial controller to smoothen out the fluctuations. So you can see that the green curve, or rather the blue curve, the blue curve refers to wind variation and the red curve refers to the output active power variation. And you can see there is a certain amount of smoothing. This smoothing is different at different wind speeds. So at 12 meters per second, if the average wind speed is 12 meters per second, the smoothing is less, while at 10 meters per second, the smoothing is more. So we have injected the same deviations, random variations in wind speed at 12 meters and 10 meters, and we find that the wind farm output is more smooth at 10 meters per second than at 12 meters per second. Similarly, if you compare a 92 kilowatt change in wind generation with a 92 kilowatt change in load in a small microgrid, then you will find that the load causes a deeper drop in frequency or a deeper change in frequency compared to the wind turbine, and this is also a result of the shaft inertia. So this is, of course, this study is done at different penetration levels, and it is found that at different penetration levels, the wind has a different ability to affect the system frequency. So two things can be concluded from this graph. One is that the wind turbine has a lower impact on the on the system frequency compared to the load change, but this impact can increase if the wind generation penetration is increasing. So that was the impact on of a event on the frequency, and the rate at which the frequency drops is referred to as the rock-off, the rate of change of frequency, which I talked about in the previous slides. In the next slide, recent work has been conducted. In fact, in IIT Delhi also we are working on this. We are looking at the ambient frequency and how does the ambient frequency depend on the amount of renewables that have already been injected into the grid. So it is found that the ambient frequency is relatively less affected. So how do we look at the ambient frequency? So now we are talking about statistical analysis rather than a analysis using differential equation systems. So in statistical analysis, we just take the ambient frequency, we collect a window of data, let's say about 6 to 8 hours of frequency data. We remove the central line, which is 50 hertz. We just removed it 50 hertz. And so we have the data of frequency deviations. And we ensure that during this window of observation, there is no big event. So we are only looking at the ambient frequency, the frequency when nothing is happening. Well, something is always happening in the grid, but nothing of significance is happening. So the changes in the frequency that you would see in that case are random changes in frequency because of random load changes and random changes in generation that are happening, which are usually unknown. Then it is found that the ambient frequency in many, especially islanded systems, not in India, but certainly in abroad like Great Britain, For instance, this data is pertaining to the Great Britain system. It is found that the ambient frequency shows a bimodal distribution. It has two modes, and this can be modeled using a Gaussian mixture model. And you can see that it has two humps at 50 and minus 50 millihertz. Then the question is what the distance between the two humps as well as the height of the two humps. The height corresponds to the number of samples. That means the probability of those humps happening, as well as the distance between the two humps. These are the two things that describe the complete statistical description of the data. And it is found that in the system in Great Britain, for instance, you have dead bands. The dead band is located with the synchronous generator. And these dead bands are typically having about 15 to 20 millihertz per dead band. So you can see on the left bottom figure, a typical dead band is shown. Dead band means that as long as the frequency remains within this, the frequency deviation remains within this dead band, the governor does not take any action. And only when the frequency goes outside the dead band, the governor takes action. So the widespread presence of dead bands results in this bimodal distribution. And the hump, the distance between the hump is very, very closely linked to the dead bands that are there in the governors. This is a very, very interesting observation, and we have tried to analyze this in the Indian context, but unfortunately we have not we are not able to link it here because of two reasons. One is that the quality of data availability in India is not so good, and number two, dead bands are not so widespread in India as it is in a islanded country like Great Britain. Then another key impact, another key, another concept that has been linked to this bimodal distribution is something called the load reversal time. So the load reversal time is a very interesting number. It basically talks about if you are looking at the grid during steady state condition. When we talk about steady state condition in class, in research, in simulation, we talk about everything at steady state. However, in real life, nothing is really at steady state. Things are always changing by small amounts. So if you look at the total load that is connected to the grid, it is never constant. It is continuously changing, but it may be changing by a very small amount. So if you look at that change in the load, over a period of time, it reverses. So it may be increasing, and then after a certain time, it reduces, it starts to decrease. So it has a certain time period of oscillation, and this time period of oscillation is called load reversal time. It is not very clear what is the source of this load reversal. Possibly, if you are having a very highly industrialized society, then the load would be very steady, very constant, and load reversal times would be large. On the other hand, if you have a society where predominantly the load is commercial or domestic, the load would fluctuate more and the load reversal time would be less. It is found that the load reversal time has an immediate impact on the frequency distribution, as shown in this graph here. Similarly, when you have primary frequency control enabled in different generators, you may have the droop, which is there, 3%, 4% droop that you may have enabled. The higher the droop, 5% droop, means the generator is reluctant to take part. 2% droop means the generator is extremely willing and capable to take part in the frequency control. So the droop also has a major role to play in the shape of this bimodal distribution. So recently in our E department at IIT Delhi, one of my PhD students has done some very interesting work on the assessment of dynamic locational grid flexibility, and this is arising out of a very, very established concept of small signal stability. Using small signal stability and of course operational flexibility, we have come up with the concept of dynamic grid flexibility. So this work has been done by Devargo. He is my PhD student and I'm presenting his work right now. So here he has looked at the impact of the fluctuations of renewable energy system generation on the power system stability and the dynamics. So he has come up with two indices. One is called the dynamic locational flexibility and the other is the inertial distribution index. So the flexibility index talks about the impact of a fluctuation in the generation, a fluctuation in the injection on the small signal stability. So you basically identify the most critical electromechanical mode in the system, look at its damping, and then find out that which bus injection affects this damping maximum. And he has done a complete analytical description of this problem, and he has come out with this index. This index can also be assessed in real time using measurements, and I invite you to have a look at his recent publications. The other index is the inertial distribution index. Now this index talks about how much the bus voltage angles and the frequencies at a particular location are excited when you have a change in the injection. How irritable the grid is at a particular location. So if you have a low inertia index, then the grid is likely to show very big oscillations, while if you have a very high inertial index, then the grid is likely to be very, very stable. The frequency and the voltage angles would be very stable. So these are all related to the active power. Right now, they can be extrapolated to the reactive power also. That I invite you, all of you, to have a look at that and see how this can be extended to include the reactive power components also. So the he has looked at the impact of the operating conditions on the flexibility index. One key operating condition that he has looked at is the tie line power flow. So if you have a very important tie line, and that based on how much that tie line is loaded, whether it is lightly loaded or heavily loaded, these indices change. And so here, this is why we are saying that the grid flexibility needs to be regularly assessed, because the operating conditions change periodically. So in large systems, like for instance, these simulations were done with the Northern Regional Power Grid. In large systems with a large number of generators, it is possible to identify some key modes. And based on those key electromechanical modes, you can form groups of generators. And these groups of generators are called coherent groups. And each group would be having very similar dynamic characteristics. So these indices, instead of specifying these indices for different buses, you can instead specify them for different groups. And you can see here on the right, top right and the bottom right, the two graphs show that for groups of generators, the indices are almost the same. And so rather than computing this index for all the generators, you can compute this index for groups of generators. These groups are shown here, for instance, and based on the available data, I'm sorry, there's a plane going up on top of me. So here you can see here, we have identified 7 groups of generators in the northern grid, and based on the indices that have been calculated group wise, we have identified the most flexible region. This is the most flexible region, central UP. Southeastern UP is the center of inertia, it is the heaviest region. Rajasthan here, it is one of the most vulnerable regions because of low inertia and low meshing. So of course, this does not reflect the picture of today because the data that we have used is more than 20 years old data. It does not reflect the picture of today. Today, there are many more transmission lines and generating stations in northern grid, so the groupings would have changed significantly. Also, the regions that we have identified are no longer applicable in today's scenario. So once you have identified these groups, uh, we have come up with the control strategy that if you are having injections, fluctuations in renewable energy injection, then these fluctuations may be compensated by appropriate action from energy storage device. So for instance, if you have a 100 megawatt generator, a 100 megawatt wind farm, which is currently generating 75 megawatts, then this 75 megawatts may suddenly drop to 72 megawatts. So the 3 megawatt fluctuation that has happened may be compensated by additional 3 megawatt generation from a energy storage that is there. The question is where to locate the energy storage device. So the energy storage device must be located within the coherent group to which the source of the fluctuation belongs. So rather than going deep into this figure here, I think this figure requires deep thinking, and I invite all of you to have a look at his publication, which is there in the IEEE Explore website. And this figure is very interesting figure, and I would suggest all of you to try to explore and understand this figure. And it is the key to what I've been talking about for the last 1.5 hours. So with that, I think we will conclude this presentation. This is just one last slide, I think. Yeah, this is one last slide that we are currently working on, and this is the uncertainty that is linked to renewable energy penetrations, renewable energy fluctuations. That means the output of the wind farm fluctuates. And this fluctuation, the uncertainty, can be described in a statistical manner. The question is that what is the source of this fluctuation? So if you have random inputs to a deterministic system, then how does the deterministic system behave? Number one. Number two, if I am measuring something out of the deterministic system, is it possible to reclaim the statistics of the original input from the output measurement? If it is possible, then it means that if I am measuring the ambient frequency and statistically describing it, then this description can be linked to the statistical description of the wind. And finally, using these kind of studies, we can eventually arrive at an accurate awareness of the state of the grid in the presence of renewable fluctuations. So I will stop here and invite questions if you have any.
Yes. Thank you, sir, for such an influencing lecture. I am from Power System from University of Calcutta, Dr. Vinay Kumar Karmakar. Sir, I could not understand that load reversal time. Means what is that? Can you please elaborate that thing?
Yeah, so load reversal time is a term which is not really used in academic literature. It is used more in industrial manuals and documents. In fact, it used to be a very common term used in 1970s and 80s. But nowadays, people are once again using it in the term in the context of renewables. So basically, let me put it very simply. Rather than giving you a formal definition, let me give you a very simple way of understanding load reversal time. So, if you are having predominantly commercial or domestic load in the society, then if you measure the feeder power,
Mm-hmm.
so if the feeder is predominantly commercial feeder, then if you measure the feeder power, then every time the light switches on or the light switches off, the feeder power would fluctuate.
Yes.
Now, this fluctuation shows a certain pattern. Obviously, if it is connected to just one generator, just one house or one establishment,
Mm-hmm.
then the fluctuation would be truly random. Random in the sense you do not know why the fluctuations are happening. But if you have diverse establishments and houses connected to that feeder, then the feeder fluctuations gradually assume a statistical distribution, a statistical character. Now, this character basically means that the fluctuations lead to the feeder power rising and eventually dropping.
Okay.
The rate at which it rises and then drops,
Mm-hmm.
this is linked directly to the load reversal time.
Okay.
If, on the other hand, your feeder is an industrial feeder on which you have industrial machinery running, and
Mm-hmm.
these machinery are constant, steady, then the fluctuations will be much, much more gradual. And
Okay.
so the load reversal time would increase in that case.
Okay. Means as I understood, this is basically the load model. You can aggregated load model.
Yeah, temporal model of the load.
Temporal, yeah. So in case of industrial load, it will be different. In case of domestic and commercial load, it is different. So
Yes, but
now,
today there is nothing called industrial. Every load is actually mix.
yeah, yes, that was sure. Now, why it is called load reversal? That I did not give. Is it ramping down rate and ramping up rate? Two
Yeah, no,
different.
it is not a rate. I'm not talking about a rate. I'm just saying that the how soon after the load rises does the load drop.
Okay, how soon the load? Okay, 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 get it.
The load will go up. So how soon will it come down after it goes up?
Okay,
Remember, this is not a very clean data. It is difficult to describe it. Of course, load reversal time would happen. You would come up with a number like 30 seconds or 45 seconds or 1 minute for the load reversal time by observing historical data over thousands of epochs.
okay, got it, sir.
So it's not very clean definition as a result. It's a statistical parameter. It's an aggregate, it's an approximate number. But it's certainly, if you are having 40, if you're comparing load reversal time of 30 seconds with 45 seconds, then I will say that the 30 seconds load reversal time refers to load which is fluctuating more compared to a load with a load reversal time of 45 seconds.
45 minutes. Yes, yes, understood, sir. Thank you.
So thank you, sir. Any other participants who want to interact with Senroy, sir? They can directly ask to sir, or even they can chat by writing on the chat box. Uh, I'm looking on the chat box, sir. Although there is some feedback, thank you, sir, for such an informative session.
Yeah, yeah, thank you for your questions. Yeah.
So
So,
actually, I'm looking on the chat box. Actually, some of participants have written their feedback over there. They have just written that the session was really informative and consists a lot of information.
okay, thank you.
So I think if any other participants have any query, they may directly ask to sir.
Yeah, please feel free to email me. Unfortunately, I don't have a slide here which shows my email ID and all, but you can visit the IIT Delhi website and you can email me. And if uh, Dr. Ganesh, you want this uh, slide also, presentation also, I can send it to you by email if you wish.
No, actually, sir, this lecture is being recorded, so
Oh,
the complete
fantastic!
recording will
Great.
be there with me.
Okay,
I'll
great.
share
Okay.
at the end of this session.
Okay. Okay. Great. Great.
So I think there is no queries from participants now. So thank you, sir. Thank you very much for this informative session, which basically consisting a lot of information. When I was preparing the schedule for this, and many of us, like Pratyasa, Rahul Dubey sir, when they have seen that, they have also told me that they will join the this meet because they want to just listen to you, sir. So that
Thank
basically
you.
reflecting that how you are wonderfully presenting. So I am very much thankful to you. Formally, I once again thank you for giving us time for this FDP. So definitely, when I'll come there for any work at IIT Delhi, I'm sure I'll be there
Sure.
with you
Sure.
to
Sure.
meet you.
Sure.
So
Sure.
thank you, sir. Thank you very
Sure.
much.
Thank
Uh,
you.
and friends, also you are very much thankful for the listening patiently. So I once again thanks all the participants and thanks to Senroy sir. Thank you very much.
Thank you very much for your attention and for your questions. So I wish you all the best. And if you have any questions or comments or you want to get in touch with me for anything, please feel free to email me at my IIT email ID. Thank you. Stay safe.
Thank you, sir. Thank you very much.
Thank you. Bye bye.
So participants, okay, thank you, Senroy sir, please. Okay, so participants are requested to please record your attendance. Was just writing the Google form which is there in the chat box. You can just open it and then fill the information required there. So that we could be able to note your attendance. So this chat will be there for only next 5 minutes. So you just try to fill it as soon as possible. So I can see that there are around more than 50 participants are there. So I hope all of you have filled the attendance. Or I'm ending this Google Meet. I'll paste this link for the attendance in the WhatsApp group which we have for this FDP, and you can also record your attendance there also. And this will be remain turned on for about more than 20 or 25 minutes. Later on, it will be we will off the taking response from there, that Google form. So if any
Do we have any
participant
more
want to
sessions
ask
today?
something from actually, there are 3 more sessions tomorrow. There is no more session for today. There are 3 sessions.
Okay.
Out of them, 2 are from the people from IIT. One is from IIT Palakkad, Kerala, and there is one more professor from NIT Kurukshetra, and there is one professor from again NIT Kurukshetra. So we have 3 sessions scheduled tomorrow. So the morning session will start at 9:30. So with this, I am very much thankful
Okay.
to all of you. And with this, I am ending the meeting. We will meet at 9:30 tomorrow. So thank you. Thank you very much to all.
Thank you. Thank you.